Find two numbers whose sum is 1 and the sum of the squares is minimized. So, and then they even they give us what that is. So note the sum of the squares is given by, and they've written it this way. So the sum of the squares is sum of the squares, SS, is equal to x squared plus y squared. So clearly what is being implied here is that we are calling the numbers x and y. So our numbers are x and y. And we want to find two numbers that add up to 1, or sum to 1, such that the sum of the squares is minimized. Okay, so we have the thing we want to optimize. That's always the first step. We want to optimize this. Well, I mean, sometimes the first step is drawing a picture, but you know what I mean. Like, we want to write down the thing we're trying to optimize. What does it say after the sum on the top line? Whose sum is 1 and the sum of the squares is minimized. Sorry, I'll try to write more clearly. So the second thing we need is our constraint. So here we're constrained by the fact that we want the numbers to add up to 1. So our constraint here is that x plus y is equal to 1. So let me edit this person. So we've got the thing we want to optimize, we've got a constraint. Now we do the thing where we take our constraint and solve for one of the variables and plug that into the other equation. So let's solve for y. So I'm going to get y equal to x plus, sorry, not y equal to x plus 1. Y equal to 1 minus x. Or if you prefer, you could also write it as negative x plus 1. Either way, it's fine. And then we're going to plug that in to the thing we're trying to optimize. So now we're going to write that the sum of the squares is equal to x squared plus, instead of y squared, we're going to write 1 minus x squared. And now we're going to expand this, right? Multiply it out so that it looks like something that's easier to deal with quadratic. So we're going to get that the sum of the squares is equal to, let's see, x squared plus, when I multiply out 1 minus x squared, oh, sorry, it looks like someone, why? What is that? Sorry, so it looked like someone was going to be trying to call. I'm getting like a weird notification from my phone suggesting I call into class. That seems strange. I'm in class already. Anyway, sorry about that. So multiplying this out, when you have something minus something squared, it's the first thing squared plus the first thing times the second thing. So it's plus 1 times 2, sorry, plus 2 times the first and second, which is 2 times 1 times negative x, which is minus 2x, and then plus the second thing squared, which is x squared. So simplifying this and writing it in kind of the standard way, I'm going to write this as x squared plus x squared, so 2x squared minus 2x plus 1 squared is 1. So that's the thing we're trying to minimize. And we know we can minimize it because it's a quadratic that opens upwards because the leading coefficient is positive, so it's going to have a minimum. So I don't know what this looks like exactly, but I know it has some sort of upward opening graph, and we're trying to find the bottom of the parabola there. The bottom of the parabola being the x coordinate is going to be our x value, and the y coordinate is going to be the sum of the squares value. That's what our vertex is going to be. So to find the x, I'm going to find the x coordinate of the vertex. That's going to be there negative b over 2a, which in this case is negative negative 2 over 2 times a, which is 2. I saw a few people on the homework say that a was 1 every time, even though it wasn't. So do be careful, right? The a value is the coefficient of x squared, whatever that is. It's not always going to be 1. I'm simplifying this a bit. I get positive 2 over 4, which reduces to 1/2. So now, what does the question ask for? find two numbers whose sum is 1 and the sum of the squares is minimized. They're not asking us what the sum of the squares is. So even though I could plug in 1/2 for x here to find the sum of the squares, they're not asking me to, right? I don't need to find this second coordinate of the vertex. What I do need to find is the other number. So I've got x is equal to 1/2. And I want y. Well, y is equal to 1 minus x. So y is equal to 1 minus 1/2, which is also 1/2, which is pretty typical a lot of the time. Like when you're trying to find the minimum value for the sum of the squares, it often ends up being that the x and the y, with the two different numbers, are the same number. So we also get y equal to 1/2. So those are the numbers that minimize the sum of the squares. And if we actually found the sum of the squares, it would actually coincidentally also be equal to 1/2. Because if you square this, you get 1/4, and if you square this, you get 1/4, and 1/4 plus 1/4 is 1/2. So that's just kind of a not always going to happen kind of thing, but happens to happen here. I think I'm going to throw in an extra one here because I think it's worth doing another one of these. So let's say we have, again, two numbers who sum to 12. Find the numbers that minimize, and I'm going to change it up a little bit here, that minimize the sum of the square of the first and twice the square of the second. Why do you, so that's a good question. So the reason I added the SS as the y coordinate is because I'm actually thinking of SS, that's kind of like my y, or it's the name of the function, right? I've got y, but I've already used y, so I'm calling it something else. I've got SS equal to x squared plus, or 2x squared minus 2x plus 1. So I was graphing this, I would be thinking of the horizontal axis as the x axis and the vertical axis as the SS axis, because that is what I'm getting out. Hopefully that makes sense, Jesus. So I'm going to continue on, but let me know, please do let me know if you have further questions. So here,
Yeah, that makes sense.
Oh, sorry. Okay. Sometimes I don't hear what people say because like I have my volume not too loud. Because some people, when they talk, it's super loud. Some people it isn't loud, so I'm always like, oh, let me turn it up. So yeah, sometimes I might ask people to clarify things if I didn't quite catch it. Also, sometimes my hearing is just terrible. So two numbers, they add to 12, and we want to find numbers that minimize the sum of the square of the first number and twice the square of the second. Okay, so I'm going to still write it as SS for some of the squares, even though it's a little bit more complicated. So we're trying to minimize the sum of the squares. And again, it's going to be the sum of the square of the first number and twice the square of the second. So that's what we're trying to minimize. X squared plus 2y squared. And here our constraint is that x plus y has to equal 12. All right, so now we want to ask ourselves, well, two questions, I guess. Which one's easier to solve for? Well, there's not an easier one. They're both equally easy to solve for. Which one's easier or less work to plug in for? I feel like it's slightly less work to plug in for x, because we're not going to have to multiply it all by 2 after we plug in. So I want to plug in for x, which means I want to solve for x. So I'm going to solve for x. So I'm going to get x equal to 12 minus y. And that is what's going to get substituted in for x right there. So I'm going to have now that the sum of the squares is equal to 12 minus y quantity squared plus 2y squared. Okay, let's multiply this out. This is going to equal, so 12 minus y squared is 144 minus 24y plus y squared plus 2y squared. Are there questions about this part specifically? I'm just doing the first thing squared plus 2 times the first thing times the second thing, which is 2 times 12 times negative y, plus the second thing squared. Negative y squared is y squared. So then simplifying this just a little bit, you get that SS is equal to y squared plus 2y squared is 3y squared minus 24y plus 144. Okay. Again, I can see that find the area. Yes to the question that was just asked, but I'm not sure in what context, like the area of what exactly. So if you want to clarify that question, I'm happy to do it. I'm just not exactly sure what you're asking for. So for this problem, right? Again, we're thinking of this as a parabola. In fact, if I want to be more specific, right? So in this parabola, our horizontal axis is the y variable and our vertical axis is the SS variable. And we're trying to find the value of y that minimizes the value of SS. So I'm trying to find the vertex of this parabola. So the y value is going to be given by negative b over 2a, which in this case is going to be negative 24 over 2 times 3, which is 24 over 6, which is 4. So the y coordinate is 4. If I plugged in 4 for y here, I would get 3 times 16 minus 24 times 4 plus 144. And that would give us what the minimum sum of the squares was. But I wasn't asked to find that. I'm going to find x. I'm going to get that x is equal to 12 minus y, which is 12 minus 4, which is 8. So x equal to 8 and y equal to 4 minimizes the sum of the square of x plus twice the square of y. And we can plug those numbers in, and you would get 8 squared plus 2 times 4 squared, which is 64, plus 2 times 16, which is 96, I think. So the minimum value is 96. So if you found the point of this, the vertex of this parabola here, where you're doing sum of squares as a function of y, that vertex coordinate would be the y coordinate in the first spot and the sum of squares coordinate in the second spot. So that when y is 4, the sum of the squares is minimized, and that minimum value is 96. Are there, sorry. Are there questions about any of this?
I have a quick question about where you got the 96 from. Like, what did you plug?
So there's 2 ways to get the 96. One way, the way I did it, which I think is the easier way, is I found the x value. So I found y, of course. And then instead of plugging in y equal to 4 here, which I could do, I found x. I got x equal to 8. And then I plugged in to here. I plugged in x equal to 8 and y equal to 4. 8 squared is 64, 4 squared is 16, 2 times 16 is 32, 64. But you could also plug in y equal to 4 here. If you plug in y equal to 4 here, here's what you get. So you get 3 times 4 squared, which is 3 times 16, which is 48. 24 times 3, which is 72, plus 144. And that I'm plugging in the wrong, 24 times 3 is 72, but 24 times 4 is what she's actually plugging in, is 96. And then 48 minus 96 is negative 48, and negative 48 plus 144 is 96. So either way, you can plug in y. So to get what the sum of squares value is at the vertex, you can plug in either the y value here or the y value and the corresponding x value here. And yes, to the person who asked the question about the area, we can definitely do one like this. That's actually, that's fine. We can do an area question. So we did do one like this on whatever the last day of class was, Friday. We can certainly talk about another one. So I'm gonna try and make it a little quick. So in the area of the largest rectangle in the first quadrant that can be inscribed under the line, I'm gonna make a line. What do I want to make the line? Sure. So let's say area of largest rectangle. So find in the first quadrant, inscribed under the line y equal to, what do I want it to be? 20 minus 5x. Is that what I really want? Let's make it 40 minus 5x. That might be slightly more interesting. Okay. Should be fine. So you don't have to draw a picture, but it's good to draw a picture. I mean, you should draw a picture. So here's my line, 40 minus 5x. It has a y-intercept of 40. Has an x-intercept of, well, let's say if I set y equal to 0, 0 equal to 40 minus 5x. 5x equals 40. 40 divided by 5 is 8. It's got an x-intercept of 8, comma 0. Now I'm trying to inscribe a rectangle of largest area. So let's say maybe here's my rectangle. It's got a base of, let's say this is the width and this is the length. Maybe you would label them different things, whatever. So I'm going to call this coordinate here that's on the line, I've gone over W and up L, so that's the coordinate WL. You can also call it XY if you want. Either way, it's fine. So what am I trying to optimize? I'm trying to maximize the area. So area is equal to, for a rectangle, length times width. Or x times y if you're using x and y. If I say x and y, this would be x times y. And now I do have a constraint. The constraint is that this point on the rectangle is on the line, meaning these points satisfy this equation. So my constraint, you can either write it as, well, W is the x coordinate, L is the y coordinate. So it would be L equal to 40 minus 5W. Or if you were using the coordinates x and y, it would just be y equal to 40 minus 5x. Either way, we're clearly going to plug in L equal to this or y equal to that, right? It wouldn't make sense to solve this for W and try and plug in for W. So we're going to get that our area now as a function of one variable, right? That's always what we're trying to do. We're trying to get the thing we're trying to optimize to be a function of one variable. And that's true whether it happens to be this pre-calculus version or when you're taking calculus next quarter, right? When you take calculus next quarter, you're still, when you're optimizing, which is until like chapter 4, you're still going to be trying to write the thing you're trying to optimize as a function of one variable. So I want area equal to the length, which is this, 40 minus 5W times W. Or, right, if you were doing it in terms of x and y, you would have area equal to 40 minus 5x times x. Then we multiply it out so that we can see it looks like a parabola or a quadrant, whatever you want to call it. This is going to be 40W minus 5W squared, but I would probably write it in the standard way, meaning I would write this as area is negative 5W squared plus 40W. And now we want to find the vertex of the parabola. So I'm going to try and find the W coordinate, which is going to be negative B over 2A. Negative B, its coefficient of W is 40, so negative 40 over 2a. The coefficient of w squared is -5, so 2 times -5. Let's see, -40 divided by -10 is equal to 4. So the w coordinate is 4, and now we have to ask ourselves, what did they ask for? In this problem, they said find the area of the largest rectangle. So you could go back and either find the length, which would be 40 minus 5 times 4, which is 40 minus 20, which is 20. And then find the area. Area is 20 times 4, which is 80. Or you could just say, well, if I'm only trying to find the area, I can just go ahead and plug this 4 in for the area equation right here and say that area, in fact, it's the vertex coordinate, it's the y coordinate of the vertex, or the area coordinate of the vertex, is equal to, plug in 4 right there. You could do it right here. I think it's easier to do it here. You get 40 minus 5 times 4 times 4. Hey, look, it's still 20 times 4, which is still 80. So for this one, right, here's the parabola. It's a downward opening parabola, something like this. And we just found the coordinates of the vertex. The coordinates being the width and the area. The x coordinate is the width of the rectangle, and the y coordinate is the area of the rectangle. Neither of these coordinates explicitly tell us what the length of the rectangle is, but we could certainly figure it out. So hopefully that gives you more idea of how to do these area ones. Let's look at, so I've got one more optimization problem, and I've got one more finding a point of it. I've got a point of intersection problem just because people often have lots of questions about how to find points of intersection. So we'll do one of those, and then we'll see how much time we've got. So the optimization questions are really, really meant to help you kind of, or get you thinking about, like, how do we take this math written in words and change it into equations and something that's meaningful, and that we can find where the maximum or minimum is, or what the maximum or minimum is. And so do be careful, right? If I was asking this question, I would say that this the maximum of this occurs when the width is 4, and the maximum value is that the area is 80. So the x coordinate, or the first coordinate, is typically the where. Where does something happen? It happens at the first coordinate. What is the value? That's the second coordinate. So this is the where, this is the value. Okay. Find the point on the graph of y equal to the square root of x that is closest to the point 8, 0. So whenever you see a question that says find the point that is closest to another point, you should be thinking, oh, if I want to make two things as close as possible, I want to make the distance between them as small as possible. So that the words we should actually be thinking of when someone says find the point that's closest is we're thinking, oh, we're trying to minimize the distance. But then we remember that it's easier to minimize the distance squared. In fact, it's preferable, right? You want this. That is what we really want. So we should draw a picture. I kind of skipped over the drawing the picture. Let's draw a picture. So y equal to the square root of x looks like our typical square root function. Looks like this. Some of the usual points we plot are 0, 0, 1, 1, 4, 2, 9, 3, et cetera, et cetera, et cetera. Picking nice x values. They're squares, and then their answers are nice integers. And I'm looking, so I'm thinking like 1, 1's about there. I don't really want to plot all that because I just want to pretend like 8 zeros over here. So there's 8, 0. And I'm trying to find the point on the graph, which is maybe right about there. I don't actually know what that point is, so I'm going to call it xy. I want to find that whatever x and y are so that this distance is as small as possible. So instead, let's write the distance. The distance between those 2 points is the square root of x minus 8 squared plus y minus 0 squared. Let's do, and so we're trying to minimize that, but we really want to minimize the distance squared, which is just the same equation without the square root. So it's x minus 8 squared plus, I'm not going to write y minus 0. That seems silly. I know that y minus 0 is just y squared. Okay. We want to minimize a thing that has 2 variables. We need a constraint. This constraint here is that this point has to be on this graph. So if we're on this graph, we know that the y coordinate is actually equal to the square root of x. So we could have actually, if we wanted to, written this point as x comma the square root of x. Whatever the way you get there, we know that y has to equal the square root of x. So we want to plug in. I suppose if you wanted to, you could also say that x equals y squared, but that seems like silly to do more work than we do. And it makes it so this isn't quadratic anymore, which we don't know how to deal with. So one thing to keep in mind when you are trying to figure out what to solve for, to plug in to the thing you want to maximize and minimize, is that for us, the final thing we get does need to be quadratic so that we can actually figure out where the vertex is. Sorry. Okay. Sorry, 1 second. I need to okay. Sorry. So I'm plugging in y equal to the square root of x. So I'm going to get that the distance squared is equal to x minus 8 squared plus the square root of x squared. So now we've got a function of 1 variable. We should be able to find where it is minimized or maximized. So let's simplify this. I've got the distance squared is equal to, let's multiply this out. We get x squared plus, sorry, not plus, minus 16x plus 8 squared is 64. Or negative 8 quantity squared is still 64. And then square root of x squared is just x. Simplifying just a little bit, this is x squared minus 16 plus x is minus 15x plus 64. And we can definitely find the vertex of this upward opening parabola. So, right, it looks like this. And if I find the vertex, the x coordinate of the vertex is going to be negative 15 over 2 times 1, which is 15 halves. You could also write this as a decimal if you prefer, right? You can write that as 7.5. I prefer fractions most of the time, but either way is okay. So the x coordinate here is 15 halves. And the second coordinate here would be whatever the distance, the minimal distance is. Actually, the second coordinate here would be the minimal distance squared. So if you plugged in this 15 halves back into here, you would figure out what the minimum distance squared was. Did they ask for that? They did not. They just asked for the point on the graph that is closest. So if I've got the x coordinate, that is the x coordinate of this point. To find the y coordinate, well, y is equal to the square root of x. So my coordinate that is closest to the point 80 is x is 15 halves, and y is the square root of x, so it's the square root of 15 halves. Usually, if they're asking you to find the dimensions of the thing or the point, right, they're not asking you to find the value that is getting maximized or minimized. It's usually pretty easy to find the second thing, right? Finding the first thing is some work, right? To find the function and find the first coordinate of the vertex. Finding the second thing is typically just plugging that thing you found back into the place that says the thing you want equal to a function of the thing you just found. Right here, we found x, and then we just said, oh, y is the square root of x. In the previous one, we found w was 4, and then we just said, oh, length is 40 minus 5 times w. So plug in the 4 there, you get the length. Yeah. Okay. So, yeah. So let's see here. So we've got, the next question. So I know there have already been some questions like this, but that doesn't mean we can't still talk about it. So I want to find the equation. So find the equation of the line. Or maybe we haven't had problems like this. Maybe I'm imagining something else. Connecting the vertex and the y-intercept of the parabola given by. I think there is a question or two like this in the upcoming homework assignment, so I wanted to make sure that everyone was okay doing it. 2 times, y equal to 2 times x minus 3 squared plus 7. So let me ask you guys. Oh, sorry, minus 7, not plus 7. Of the two things I'm asking to connect, which are the vertex and the y-intercept, which of those two things is actually easier to see for this particular parabola? Is it easier to see the y-intercept right off the bat, or is it easier to see the vertex right off the bat? I would agree, Nicole, vertex. And I imagine most people are thinking that as well. Right? This is written in the vertex form, and so we can see that the vertex is just the point. X has to be 3. If x is 3, then y is, well, if x is 3, this part's all 0, so y is 0 minus 7, which is negative 7. On the other hand, the y-intercept is actually a little bit harder to see, or there's more work, right? If the parabola was written in, like the standard form, the ax squared plus bx plus c, and I'm probably interchanging the names accidentally. If you had a parabola that's not the same as this one, if you had a parabola that was like x squared minus 5x plus 6, it's really, really easy to see that the y-intercept is 6. If you set x equal to 0, you get y equal to 6. Here, it'd be more work to find the vertex. You'd have to do the negative b over 2a and all that kind of stuff. So here, the y-intercept, you're going to set x equal to 0, and we're going to get y equal to 2 times 0 minus 3 squared minus 7, which ends up being 2 times negative 3 quantity squared is positive 9 minus 7. So you get 18 minus 7, which is 11. So the y-intercept is the point 0, 11. Now we're not done. We found 2 points. Now we're being asked to find the equation of the line that goes through those 2 points. So let's see here. I want to find the equation of the line, so I'm going to find the slope. That's going to be the difference in the y's or the difference in the x's. You can either do this y minus that y over this x minus that x, or vice versa. This y minus this y over this x minus this x. I usually like to try and subtract in the direction where more things are positive. So I would probably do 11 minus negative 7 over 3. Maybe I made the wrong. Sometimes one of them has to be negative. Not always, but sometimes. Over 0 minus 3, right? That minus that over that minus that. And I'm getting 18 over negative 3, which is negative 6. So there's my slope. Now, I could do this a variety of ways. I could say, right, y equals mx plus b and plug in a point, solve for b. But I've already been given the y-intercept. So I could actually just jump straight to saying, oh, y equals negative 6x plus 11. And know that's right because, well, one, if I plug in 0 for x, I get 11 for y, so that works. And I can also check here, if I plug in 3 for x, negative 6 times 3 is negative 18. Negative 18 plus 11 is negative 7. I get negative 7 for y. But you could also start it off with, y equals negative 6x plus b. And if you really wanted to make it more work for yourself, you could plug in this for x and this for y, and then solve for b. But if you already know the y-intercept, you can just end up with it for y-intercept. Yeah. And I guess we could graph these. I would kind of want, yeah, let's go ahead and graph them. Do I really want to graph them? Yeah, I guess I do want to graph them because I want to talk about how you find normal things. So here's what we've got. We've got y equal to 2 times x minus 3 squared minus 7. That is a minus, right? Yes. And we've also got y equal to negative 6x plus 11. And we know that they intersect at 3, negative 7, and 0, 11 are points of intersection. So I'm not going to try and be like super precise, but I'm going to be trying to be a little precise. So let's say this is 0, 11 here. And let's see, 3, so I'm not going to go down quite as much as that. So let's say maybe right here is our other point, 3 comma negative 7, which I'm not going to label just yet. So I know I have a line that goes through these 2 points. So I'm going to try and graph, and then I'll maybe fix it. That turned out better than I expected. I feel like I made this a little too long. Oh, well. Such is life. And then I have a parabola, which goes through this point, and this is the vertex of the parabola. So this is probably not going to look perfect. Oh, well. Well, I have to say I'm surprised at how good that turned out. So the only thing, if you're being asked to like graph this completely, maybe fill in all the things. So here's our point 3, negative 7. The other things we probably want to find are the x intercepts of both the parabola and the line. Which are not too terrible, but they are a little bit of work. So for the line, the x intercept for the line, you would set y equal to 0. So we end up with 0 equal to negative 6x plus 11. I'm going to add 6x. 6x equals 11, so x equals 11 over 6, which is just a tiny bit smaller than 2. So this point here would be 11 over 6 comma 0. And then for the what I really want to do is actually show you how to find the x-intercepts for the other one. So there's something actually kind of special about this. So for y equal to 2 times x minus 3 squared. And of course, we're going to set y equal to 0. So here's what I want to say. The x-intercepts here are not going to be nice. I know that because I know that 7 is not a square number, really. So one way you can find the x-intercepts is you could multiply this all out. You would get something like, I don't know, 2x squared minus 12x plus 11. And then you could use the quadratic formula. Not my favorite, but it's fine, it works. But when you have something written in the completed square form like this, there's actually kind of a faster way to find the x-intercepts. I'm going to solve for x. So I'm going to add 7. 7 equals 2 times x minus 3 squared. Divide by 2. 7 halves equals x minus 3 squared. And then we can take the square root of both sides using the square root property, meaning that x minus 3 is going to equal plus or minus the square root of 7 halves. And then we can add 3 to both sides and get that x is equal to 3 plus or minus the square root of 7 halves. Which is where this is 3 plus the square root of 7 halves. then this point here is 3 minus the square root of 7 halves. So that is what we've got going on there. You don't have to do it this way when you're finding the intercepts that are probably given in the vertex form, but it's kind of nice. So just want to let you guys know about that. All right. 4 minutes does not seem like the right amount of time to be. Yeah, I don't want to waste time. I also feel like it's kind of weird to start a new section. Let's go look real quick here. Let's see. Yeah, let's go. So I'm going to start talking about just the beginning of class E, and then we'll definitely revisit this tomorrow. So E for exponents. I definitely feel like the person who organized these notes definitely tried to like make some of the letter names match up with like the first letter of the topic. Okay, so exponents. What do exponents really mean? Well, when I think of exponents, what I'm really thinking of is repeated multiplication. So when someone writes 2 to the third, even though we know the answer is 8, because we know that 2 to the third means 2 times 2 times 2. And in a similar way, 5 to the fourth means 5 times 5 times 5 times 5. So you can see, I mean, it's really one of the things that exponents were there is they're just abbreviations. If I want to write 2 to the 10th, I don't want to write 2 times 2 times 2 times 2 10 times, right? That just seems silly. So instead, we came up with this notation to help us kind of make things easier. We also have radicals. Something like the cube root of 64, for example. So when you write a radical, there are 2 pieces. There's obviously the radical, which is just the this symbol, right? So this part here is the radical. And this number here is the index. Which, I mean, we don't really have to remember this terminology, but it does mean something. So what this means, right? Exponents are repeated multiplication. This is kind of the opposite of that. It's asking what repeated multiplication would you have to do this number of times to get this number. So here we're asking what is the number, or what number multiplied by itself 3 times, and the 3 is exactly coming from the index, equals 64. Right, that's what this expression actually says. And we know that the cube root of 64 is equal to 4 because 4 times 4 times 4 equals 64. In the same way, right? So I should say when the index is 2, what does it say in green? Right here it says radical, pointing, so this symbol is the radical here. And then the number up there is the index. That's what that was, it says index. So in a similar way, we can say that the 5th root of 32 is equal to 2 because 2 times itself 5 times, which is 2 to the 5th, is 32. And I'll say one last thing is that, and you guys know this already, but I just want to make it clear, right? When you write a square root, so the square root of 25, we don't write the index of 2 there, right? You could write this, but we don't. It's kind of like the same way it's like you don't write 5 to the first when you write 5, you just write 5. So this means that's equal to 5 because 5 times 5 equals 5 squared equals 20. So that's the beginning of exponents and roots, or radicals, also called roots. we will definitely continue to talk more about this in class tomorrow.